Good evening, everyone. It is our May Speakers Night for 2023. Welcome to Rask Toronto Centre. We are online tonight, and I'm Dr. Elena Hyde, the second Vice President of our Rask Toronto Centre. This is our Speakers Night presentation. Please note that this meeting is online only and not at the Ontario Science Centre. Our president, Tom Luton, will be talking about various programs and interesting things later on this evening. But first, we have our very special event to kick off. So before we get started, I would just like to take a moment to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here, together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. So, to get us started today, I'd like to go ahead and introduce our fantastic speaker. If you've missed the, I suppose, web announcements or the Twitter blasts, we have tonight a very great speaker, Conor Hayes, a PhD candidate in physics and astronomy at York University in Toronto, Ontario. They are working under the supervision of Dr. John Moores, and they've received their Bachelor's of Science in Astronomy and Astrophysics from The Ohio State University in 2020, the Master of Science in Physics and Astronomy from York University in 2022, and their current research focus is now on understanding all about water, apparently. So transport, storage, and other volatile molecules on the moon. In addition, they're a member of the environmental science team on the Mars Science Laboratory Curiosity rover mission, just in case that's not a long enough, I suppose, accolade. So they serve as environmental science theme lead during mission operations planning several times each month. And just in case you're interested in sort of following along a bit with the topic of this talk tonight, the moon, well, right now the moon is currently rising just before the sun in Toronto, so it will be a challenge to see it only 2% full. If you're looking for bright targets tonight to kind of follow along in spirit, Mars and Venus are up just after sunset, so it might be a little bit easier to spot if you're in Toronto, especially. And just to phase out of this introduction and get to our satellites on, so to speak, I'll go ahead and pass this away to Connor now. So please take us away to our lunar neighbor, Connor.
Thank you, Elena, for the introduction, and good evening, everyone. I'm very excited to be here tonight, talking to you about one of my research topics that I've been looking at both through my master's and as well now into my PhD about the history of lunar water from Harold Urey to Artemis and beyond. So I guess let's get started. All right, so as we all know, our planet is home to a truly astonishing collection of living beings that are so varied in their physical characteristics that it seems almost impossible to believe that they all share a single common ancestor. Now, despite all of this incredible amount of diversity, there is in fact a small set of basic needs that all known forms of life have in common. Perhaps the most fundamental of these needs is liquid water. Water plays a critical role in some of the most foundational parts of biology, like the metabolic processes that allow us to turn food into energy and photosynthesis in plants. Although we have found forms of life that have adapted to live in extremely arid environments for extended periods of time, every living creature that we know will eventually die without sufficient water. For this reason, the presence of water is one of the first things that we look for when assessing the potential habitability, either past or present, of extraterrestrial worlds, with the range of distances around every star where temperatures are right for liquid water to exist being referred to as the habitable zone. So, one of the places in our own solar system where the potential for water and intelligent life haunted popular culture for many years is our red neighbor, Mars. The earliest telescopic observations of the red planet by Giovanni Cassini, William Herschel, and others in the 17th and 18th centuries revealed the presence of clouds and polar ice caps that grew and shrank with the seasons, implying that Mars had an atmosphere that contained at least some amount of water. However, attempts to verify these theories were challenged by the fact that telescopes at the time did not have the resolving power required to observe the surface in any meaningful detail. Consequently, the best maps we had for many years were like this one from Giovanni Schiaparelli in 1886. Rather than any distinct surface features, we could only see these sort of vague blobs of dark and light regions. Notable on this map are these linear, narrow features, which Schiaparelli dubbed in Italian canali. Properly translated, this means channels, which is a fairly neutral term that doesn't make any attempt about any inferences about their origin. Unfortunately, the term was often translated into English as the much less neutral canals, which does specifically imply an artificial origin. Martian canals were popularized in large part thanks to Percival Lowell's maps of the early 20th century, which he often accompanied with these fanciful stories of an intelligent civilization on a dying planet, digging these extremely lengthy canals from the polar regions in an attempt to feed water from the polar ice caps to cities in the equatorial regions. The idea of Mars as a home to a civilization not unlike our own would not die until the mid 1960s, when the Mariner program was able to send back the first detailed images of Mars' surface. These images were of a desolate planet covered in craters, with a tenuous atmosphere and no liquid water on its surface at all. There was no evidence that any kind of advanced civilization had ever existed on Mars, though some were quick to point out at the resolution of these data, finding evidence of humanity's existence on Earth, had the Mariner probes flown past us instead of Mars, would be challenging at best. Although the dream of intelligent Martians is well and truly dead, the hunt for Martian life is very much still ongoing, even if we are now looking for bacteria rather than ETs. Take a look at the landing locations of NASA's four most recent Martian rovers. The fingerprints of our need to answer the question of whether or not we are alone in the universe are sort of all over these site selections. At the Opportunity landing site, we can see high abundances of hematite, which is a mineral that on Earth typically forms in environments that were subjected to water at some point in the past. Opportunity's twin Spirit landed in Gusev crater, where you can see this large river channel running out of the crater down and through the surrounding terrain. Both Curiosity and Perseverance landed in craters with inflow channels and potential river deltas, potentially suggesting that Gale and Jezero were at least partially filled with water in the past. Now, despite how much I've talked about Mars so far, we're not actually here tonight to talk about Mars. We're actually looking much closer to home at the moon. Because the Earth-Moon distance is much smaller than the Earth-Mars distance, we've never had the same kind of difficulties interpreting its surface features. Even with just a pair of binoculars, it is possible to resolve the lunar surface in reasonably good detail. This here is actually an image of the moon that I took several years ago from my backyard with a pretty small, maybe 4-inch or so telescope. Even in this image, it's pretty obvious that the moon has no atmosphere and no liquid water on its surface, a view that has been widely accepted without any major controversy for many centuries. There were occasionally some more out there proposals put forward, like one from Peter Andreas Hansen in 1854, where he suggested that the moon's center of gravity was offset from its physical center by several dozen kilometers, which he theorized would allow an atmosphere and water to exist on its far side. But these ideas were never taken particularly seriously. And then in the 1960s, at about the same time that the Mariner probes were killing the Martians, one man dared to challenge the dry moon status quo. This man's name was Harold Urey, and the weight that his opinion carried in the scientific community was not insubstantial. Just to list off some of his accomplishments, in 1934, he was awarded the Nobel Prize in Chemistry for his discovery of deuterium, an isotope of hydrogen with one proton and one neutron. During World War II, he participated in the Manhattan Project, where he helped develop the gaseous diffusion method of enriching uranium. His name forms half of the famous Miller-Urey experiment, where bolts of electricity were run through a mixture of gases simulating the early terrestrial atmosphere, demonstrating that amino acids, which are some of the building blocks of life, could have been spontaneously generated on the early Earth through entirely non-biological means. He also came up with the Urey reaction of the carbonate silicate cycle that helps regulate the amount of carbon dioxide in our atmosphere. And finally, and most important to us here, In the pre-Apollo era, he was a major force pushing NASA to prioritize exploration of the moon. This was clearly not just some guy with a wild idea. Urey was both extremely accomplished and well respected within the scientific community. So, what exactly did he say? So, Urey was motivated by the results of the Ranger and the Lunar Orbiter programs, which sent a series of probes to take the first close up pictures of the moon. Urey saw features like filled craters and these sinuous rills that seemed to be the result of some kind of flowing liquid. Although he was initially reluctant to say whether this liquid was water or lava, he eventually became absolutely convinced that the features seen by Ranger were the result of flowing water, writing in 1967 that the evidence supporting his theory was both overwhelming and extremely obvious. A stance that upset many of his fellow scientists, who levied attacks both against his theories and against Urey himself that were not always the most professional, which he alludes to here, stating that others believe that the evidence that he sees in the Ranger photos are in fact created by lava, dust gas, or possibly even vodka, referring to assertions by some that the only logical explanation as to why Urey so vigorously defended the idea of liquid water on the moon was that he was phenomenally drunk at all times. Unfortunately for Urey, the Apollo program that he helped advocate for ended up being his downfall. Samples returned to Earth by the Apollo astronauts contained ample evidence that not only is the moon currently dry, there was almost certainly never any substantial water on its surface. For example, Apollo 15 landed near Rima Hadley, which you can see in this photo, similar to the other sinuous rills that Urey had argued were an analog to terrestrial river channels. The Apollo 15 samples were clearly igneous in origin, suggesting that the lunar rills were carved by lava and not water. Additionally, Apollo returned samples of lunar vesicular basalt. So, this is basalt that formed through the cooling of lava that contained dissolved gases. As the lava cooled, the gases expanded, leaving behind a rock full of vesicles, or all these little holes that you can see here. If the dissolved gas was water vapor, then one would expect to see hydrated minerals in the vesicle walls. However, the return samples were almost completely devoid of the minerals. Although there was evidence for a small amount of water in these samples, it was nowhere near enough to support anything even close to what Urey had been proposing. Almost overnight, all of the work that Urey had bet his professional reputation on collapsed around him. Apollo had confirmed the status quo understanding of the moon as a body whose surface had never been subjected to any kind of aqueous alteration, despite the morphological similarities that Urey's analysis had relied on. To his credit, in the face of such overwhelming evidence against him, Urey admitted that he had been wrong, writing in 1971, "Unless we get new evidence suggesting otherwise, we should not believe that water existed on the lunar surface in significant amounts at any time in the past." Although this was almost certainly deeply embarrassing for him, both in a personal and in a professional sense, at the end of the day, it is always good science to let the data reshape your theories rather than to let your theories shape your interpretation of the data. So, although Urey was wrong about flowing water on the lunar surface, another of his theories motivates much of modern lunar exploration, including the Artemis Base Camp site selection. This is the theory of permanently shadowed regions, or PSRs, though Urey would unfortunately die in 1981, over a decade before this theory would see any kind of confirmation. So, to understand what a PSR is and why we should find them interesting, we first need to understand what causes seasons here on Earth. Our planet's rotational axis is tilted about 23.5 degrees relative to our orbit around the Sun. As a consequence, the latitude of the subsolar point, or the location on the Earth where the Sun is directly overhead, drifts north and south over the course of a year. At the northern winter solstice, as you can see here on the left, the subsolar point is as far south as it gets, meaning that the Sun appears lower on the sky for those of us here in the northern hemisphere, reducing the amount of solar energy delivered to the surface and making it colder. At the northern summer solstice, here on the right, the exact opposite happens. The subsolar point is as far north as it gets, the Sun appears high on the sky, and the increased solar energy warms the surface and the atmosphere. We can see how dramatic this effect is by looking at the paths that the sun takes across the sky at two locations during the solstices. At 85 degrees north on the left, the sun never sets in the summer and never rises in the winter. Here in Toronto, the summer sun comes within 20 degrees of passing directly overhead, while the winter sun is not even 25 degrees above the horizon. The moon's rotational axis is also tilted by, though only by about 1.5 degrees. This results in a much smaller seasonal effect, which we can see by looking at the same latitudes as we did on Earth. Near the poles, the sun is skimming just over the horizon for the entire year, while at mid-latitudes the sun follows the same middling path across the sky. The interesting observation here is that the elevation angles are measured with respect to the so-called zero elevation horizon. That is the horizon that you'd see if the moon was a perfectly smooth sphere. The moon, notably, is not perfectly smooth, and local terrain features could cause the actual horizon that you observe on the surface to differ substantially from this idealized horizon. Imagine, for example, that you were standing near the North Pole and there was a large mountain range to your south. The mountain range could produce a horizon that looks something like this. Notice that the sun is always below the horizon created by the mountains, meaning that it will never appear to rise at any point during the year. You have now found yourself standing in a PSR. Lunar PSRs form most frequently within craters located near the poles, as they have the perfect combination of a low elevation sun and high elevation local terrain. Imagine a crater like this one, where one portion is illuminated when the sun rises. Over here, while the rest of the crater is in shadow. Now, when the sun has moved to the other side of the sky and is setting, we have now swapped which side of the crater is being illuminated and which is in shadow. If we overlay the two, there is this bit in the middle that is shadowed at both times and is thus never exposed to the sun. This central part of the crater floor is the PSR. So, what Urey and others after him realized that was because the moon has no atmosphere to help move heat between the illuminated and shadowed portions of its surface, PSRs would be much colder than the surrounding terrain. Here we can see this illustrated in a map of maximum summer temperatures at the lunar south pole, as measured by the Diviner Lunar Radiometer, which is an instrument on board the Lunar Reconnaissance Orbiter, or LRO. While much of the surface peaks at around 200 to 300 Kelvin, the PSRs show up as these dark blue regions with temperatures below 120 degrees Kelvin. Keep in mind that these are the maximum summertime temperatures, so the PSRs will spend most of the year at temperatures even lower than this, potentially even as low as 30 to 40 Kelvin. To understand why these consistently low temperatures are interesting, let's take a brief journey back to high school chemistry and the pressure temperature phase diagram of water. So this diagram tells us what phase water will be in for a particular combination of the pressure and the temperature. If we overlay the typical daytime pressure and temperature of the moon, we can see that any water must exist as a gas. However, you might notice that the pressure line here does intersect with the solid gas sublimation curve at a temperature of about 110 Kelvin. If the temperature drops below this point, then water will suddenly be able to accumulate on the surface as ice. This is what makes PSR scientifically interesting. They are so cold that they can act as these so-called cold traps, where molecules like water that would rapidly sublimate away in the sunlight can accumulate over potentially billions of years. So why exactly should we care about the ability of PSRs to cold trap water? Well, from a purely academic perspective, any ice deposits within PSRs may be, billions of years old, potentially preserving a record of the early era of our solar system's formation. From a more practical perspective, PSRs are a promising target for in situ resource utilization, or ISRU. ISRU is motivated by the fact that ferrying materials like water from Earth to a crude base on the moon will be very expensive. If we can find and extract those same resources on the moon, then we can save on those costs, making the idea of a long term crewed mission to the moon much more financially plausible. So, of course, just because PSRs can cold trap water does not mean that they actually do. Following the initial proposal of the existence of PSRs, there were a number of attempts to quantify how much water they might hold. Using different estimates for the amount of water delivered to and lost from the moon, all these various papers were published quoting values anywhere from no ice in any PSRs to deposits hundreds of meters thick in every PSR. This is the range of values so wide as to be functionally useless, suggesting that we needed to go collect actual data rather than just relying on estimates. So these efforts began in the mid 90s with radar surveys. Radar can be used to look for ice because every time a radar signal scatters off of a surface, its polarization direction reverses. This can be characterized by the circular polarization ratio, or CPR, which is the ratio between the returned signal polarized in the same versus the opposite direction as it was transmitted. A dry, rough surface will scatter the signal multiple times in such a way that the return signal is a mixture of light that is polarized in both the same and the opposite direction as it was transmitted, resulting in a CPR values typically between about zero point 0.5 and 1. An icy surface, however, will preferentially scatter light back in the direction that it came, resulting in a signal that is preferentially polarized in the same direction as it was transmitted for a CPR greater than 1. The first radar survey of the lunar pool was conducted by the Clementine spacecraft. Clementine was actually not designed to take radar measurements. The idea that water could exist on the moon in any appreciable amount was still regarded with skepticism at this point of time, so looking for water was not part of its intended mission. Despite this, the mission team was able to rig up a bistatic radar experiment with some creative thinking. To conduct the experiment, Clementine would turn its radio transmitter towards the moon and fire a series of pulses at the surface. These pulses would then reflect off the moon and towards Earth, where they would be detected by radio telescopes on the ground. The initial results from Clementine seemed promising. During the 4 orbits during which the experiment was conducted, those where the spacecraft passed over the poles returned a higher CPR than those that didn't pass over the poles, suggesting that polar ice might be present. However, the authors of this paper in which this result was published do admit that they didn't collect enough data to definitively come to this conclusion, and it's entirely possible that the higher CPRs they observed were the result of a blocky surface rather than the presence of ice, as large rocky blocks can scatter radar signals in a manner that mimics ice. These concerns were validated with a more extensive radar survey conducted several years later using the Arecibo telescope. These two figures show the area of both poles imaged by the survey. Arecibo was able to look directly into several of the large PSRs like these seen here, thanks to the fact that the Earth appears higher on the horizon at the poles than the Sun does. When we look at the CPR values measured here on this figure on the right, the brightest white areas, which could be consistent with water ice, appear in small areas scattered all over the place rather than concentrated within the PSRs. Because many of these points occur on the sunlit terrain where ice would not be stable, further doubt was cast on the idea that Clementine actually detected ice. Arecibo also measured the CPRs of several craters at equatorial latitudes and found similar values that were detected at the poles, once again suggesting that the enhanced polar CPRs were the result of surface roughness rather than ice. Another way that we can look for ice on the moon is by taking advantage of a phenomenon called cosmic ray spallation. When a cosmic ray penetrates the lunar regolith, it can sometimes impact an atom and release a spray of high energy neutrons. These neutrons then travel up to the surface and into space where they can be detected from orbit. Occasionally, these so-called spallation neutrons can hit other atoms as they travel towards the surface. If the atom they impact has much more mass than the neutron, for example, a carbon or an oxygen atom, then the neutron will just simply bounce off without losing much energy. However, if the atom and the neutron have approximately the same mass, as is the case with hydrogen, then there will be a very efficient transfer of momentum between the neutron and the atom, resulting in the neutron losing much of its energy. It will then emerge from the surface as a much lower energy neutron. If we count the number of neutrons with different energies coming from the moon's surface, a technique known as neutron spectroscopy, an area with many more low energy neutrons and many fewer high energy neutrons could indicate that there is a concentration of hydrogen atoms below the surface at that location. Note that I have specifically been saying hydrogen atoms and not water. This is an important limitation of neutron spectroscopy. It is sensitive to hydrogen generally and not water specifically. If we want to claim that our measurements are the result of water and not some other hydrogen-bearing compound, then we must rely on other data. For example, if we can correlate the locations of the neutron-suppressed regions with the locations of PSRs, then we can make a more plausible argument for water being the cause of the neutron suppression. The first mission to conduct neutron spectroscopy was Lunar Prospector, with its creatively named Lunar Prospector Neutron Spectrometer, or LPNS. Although LPNS did detect significant neutron suppression at both poles, as can be seen here in these sort of blue regions, the instrument's resolution was unfortunately not good enough to make that spatial correlation that we need. If we zoom into the south pole and highlight the location of some of the larger PSRs, we can clearly see that the neutron suppression appears to be both inside and outside of PSRs. While this could indicate the presence of ice buried deep below the surface where it would be protected from the sun, the resolution simply is not good enough to make any definitive conclusions. In the 2010s, we got the higher resolution data that we were looking for thanks to the Lunar Exploration Neutron Detector, or LEND, on board the Lunar Reconnaissance Orbiter. The LEND dataset have at least 5 times the resolution of the LPNS data, allowing us to more convincingly correlate the neutron suppression regions with the PSRs. Here we can see that the regions with the highest neutron suppression, and thus the highest water equivalent hydrogen concentrations, clearly lie within the PSRs at Cabeus, Hayworth, and Shoemaker craters. Interestingly, these data suggest a very heterogeneous distribution of ice within the PSRs. Other than these 3, none of the other PSRs seem to show signs of neutron suppression consistent with subsurface ice, meaning that whether or not we find ice within a PSR might depend on which PSR we are looking at. Note here that I've also indicated that the high resolution of the LEND data has been the subject of some debate. Shortly after these results were published, there were concerns raised that LEND did not properly account for the background signal of neutrons coming from no particular direction. The concern was that if some of the measured signal was actually from the background, LEND would actually have a resolution similar to LPNS, which would invalidate the otherwise apparently obvious spatial correlation between the neutron suppressed regions and the PSRs. A third way that we can search for ice is through direct imaging and reflectance measurements. This basically involves taking pictures of the surface and then looking for ice in those pictures, taking advantage of the fact that ice and lunar regolith look different at different wavelengths. Here we can see laboratory imaging of crushed ice and lunar regolith simulant in the visible and in the ultraviolet. The ice in the top left and the bottom right circles looks brighter than the regolith in the visible, but darker in the UV. Of course, this requires the ice to actually be present on the surface. Unlike neutron spectroscopy, if the ice is buried below the surface, then direct imaging cannot detect it. Now, obviously, if you can't see it, you can't see it. So there are 2 methods of conducting these measurements, passively and actively. Passive imaging relies on the light that is already present in the environment, like taking a picture of a dark room with your camera's flash turned off. Active imaging is the opposite, using a laser or other light source to artificially illuminate the terrain before taking the picture, like turning your camera's flash on. So we'll begin with passive imaging. You may be wondering how we can passively image PSRs. Passive imaging relies on the natural illumination, and PSRs are, by definition, not illuminated. As it turns out, while PSRs are very dark, they are not perfectly dark. One major source of illumination that we can rely on is what we call singly scattered sunlight. This is sunlight that is bounced off of sunlit terrain into the PSR and then back up to where our spacecraft can detect it. It is very faint, but bright enough that it can be used with a sensitive enough camera. The first direct image of the interior of a PSR was taken with the terrain camera on board the Japanese Kaguya spacecraft. So here on the left, we can see the TC image of Shackleton crater as it appears with a normal exposure settings. There is a brightly illuminated sliver of the crater wall, while the rest of the crater, which includes the PSR, appears to be completely black. However, if we pull the exposure up, The illuminated wall becomes completely blown out and overexposed, but we can suddenly see all kinds of detail within the shadowed portion of the crater. The Lunar Reconnaissance Orbiter's narrow angle camera used a similar technique to construct scattered light mosaics of many of the largest PSRs at both poles. Here I'm showing the mosaics of the Shoemaker and the Faustini PSRs. Unfortunately, neither the TC nor the NAC images showed any evidence of large surface exposed blocks of nearly pure water ice. These results suggest that either the ice is not present at the surface at these locations, or if it is mixed with the regolith in such a way that the reflectance of the mixture is indistinguishable from the reflectance of ice-free regolith. Another passive reflectance instrument is the Lyman Alpha Mapping Project, or LAMP, also on board LRO. Unlike the TC and the NAC mosaics, LAMP looks in the near ultraviolet using an even fainter source of light. Solar Lyman alpha photons scattered off the interplanetary dust, as well as light from UV bright stars. So LAMP looks in these two spectral bands, the on band, where ice is very dark, and the off band, where ice is very bright, which you can see in the plot of reflectivity versus wavelength here on the left, where the dashed line is the reflectivity of the ice, and the solid line is the reflectivity of the regolith. On the right, we can see the reflectivity of various mixtures of ice and regolith. As more ice is added to the mixture, the off-band reflectivity quickly increases, while the on-band reflectivity slowly decreases. By dividing the off-band reflectivity by the on-band reflectivity, we can quantify how much ice must be present to explain the LAMP measurements. So here's a map of that off-on reflectance ratio plotted against the maximum surface temperature. We can see that the areas with the high off-on ratio, sort of the light blue colors here, correlate well with the areas that are cold enough to trap water, which are the sort of dark black areas. Um, Although, much like the lens results, the potential distribution of this ice is very patchy and heterogeneous, with not all PSRs showing evidence of surface exposed water ice. These results indicate that in areas where ice might be present, it will be at concentrations of about 0.1 to 2% by weight if it is mixed with a regolith, or potentially as high as 10% if the deposits are nearly pure rather than mixed. So active reflective measurements of PSRs have been taken by the Lunar Orbiter Laser Altimeter, or LOLA, yet another LRO instrument. LOLA's primary purpose is to create terrain maps of the moon by firing a series of lasers at its surface, and then using the time that it takes for the light to travel from the spacecraft to the ground and back to determine the distance. However, LOLA can measure not just the time, but also the relative strength of the transmitted and received laser pulses, meaning that it can determine how reflective the surface is. So LRO is in a polar orbit around the moon, meaning that each orbit takes it over both poles. Because the lunar south pole lies on the rim of Shackleton crater, this means that Shackleton has an extraordinarily high density of LOLA measurements, allowing us to create some of the highest resolution maps we have of any location on the moon. A few of these maps are shown in this figure, including the terrain, the time spent in sunlight each year, and of interest to here, at the bottom right, the reflectivity. So LOLA measurements indicate that the walls, and to a lesser extent the floor of Shackleton, are more reflective than the surrounding terrain, which could indicate the presence of water ice. However, this seems unlikely for several reasons. First, none of the other data sets we have discussed up to this point have shown evidence for surface exposed ice at Shackleton. Second, the walls of Shackleton are particularly steep for a lunar crater. This is important because the steep slope allows for material to slide downhill more easily, a process known as mass wasting. The moon's surface is particularly dark as a consequence of impacts with micrometeorites, so mass wasting on the walls of Shackleton would regularly expose fresh material from the subsurface that has not been exposed to micro impacts and thus would be brighter. The interior of Shackleton is also more protected from micrometeorites thanks to its geometry, so fewer impacts might occur within it generally, leading to the surface being brighter overall. The final method that has been used to look for ice from orbit is infrared spectroscopy, most notably done by the Moon Mineralogy Mapper, or M-Cubed, on board the Indian Chandrayaan-1 orbiter. So IR spectroscopy relies on the fact that water ice has three absorption features in the infrared at 1.3, 1.5, and 2 microns. IR spectroscopy has a leg up on the other methods that we've discussed because these absorption features allow us to differentiate between water and other hydrogen-bearing compounds, as well as between surface-exposed ice, water absorbed on the surface, and hydrated minerals. If we detect all three absorption features in the spectra, then we can be reasonably confident that surface-exposed ice exists in that location. So what M3 found is that approximately 3.5% of PSR pixels have spectra indicating the presence of water ice, which is consistent with the patchy distribution implied by other datasets. If we compare the locations where M cubed indicated the presence of water ice with those same locations in these other datasets, we can further convince ourselves that the M cubed measurements are consistent with ice. In each of these histograms here, the blue curve indicates the points where M cubed measured water, and the black curve is all shaded regions at the poles. Looking at surface temperatures here on the top row, we can see that nearly all of the M cubed detections lie below the water stability temperature, while the other points average at much higher temperatures. In the middle row are LOLA reflectance measurements, where the M cubed points generally appear to be higher, as we'd expect to see with ice. Finally, in the bottom row is the lamp off on ratio, where the M cubed points are on average higher than all of the non-ice points. Combining all of these data together, we get this map of superficial ice exposures as constrained by M cubed, LOLA, Diviner, and LAMP. Once again, we see that the distribution of ice is very patchy and heterogeneous, although perhaps slightly less so than any of the datasets indicate separately. Of course, the easiest way to determine whether or not water exists on the surface is actually to go down ourselves and look for it. The best that we've managed to do so far occurred in 2009 with the Lunar Crater Observation and Sensing Satellite, or LCROSS. LCROSS was a kinetic impactor mission targeting the Cabeus Crater PSR, one of the coldest locations on the moon. In this temperature map, the planned impact site is marked with a white star, and it never experiences temperatures higher than approximately 50 Kelvin, making it a prime target to examine for the presence of ice. So LCROSS consisted of two parts. The LCROSS shepherding spacecraft, which housed all of the scientific instrumentation, and the LCROSS impactor, which was the expended upper stage of the Centaur rocket booster that helped bring both LCROSS and the Lunar Reconnaissance Orbiter to the moon. On October 9th, 2009, the 2,300 kilogram Centaur booster impacted the lunar surface at about 2.5 kilometers per second, excavating a crater that was expected to be nearly 20 meters across and 3 to 5 meters deep, and launching a plume of material high above the surface. The shepherding spacecraft then flew through that plume and spectroscopically analyzed its contents before it too impacted the moon several minutes later. Telescopes all around the world were pointed at the lunar South Pole, as it had been predicted that the impact might actually be visible from Earth. Unfortunately, the plume ended up being less visually stunning than modeled, but the data returned by the shepherding spacecraft before it met its fate more than made up for it. The spectral data indicated that about 5% of the ejected material was water, directly confirming for the first time that water does actually exist within a lunar PSR. Even more exciting was the fact that water was not the only volatile molecule that LCROSS detected in the impact plume. LCROSS also confirmed the presence of molecules like carbon dioxide, hydrogen sulfide, sulfur dioxide, methane, and ammonia, opening up a brand new chapter in lunar exploration. So I'll finish this little history lesson off by noting one of the more unusual discoveries in the search for lunar water. In October 2020, it was announced that the Stratospheric Observatory for Infrared Astronomy, or SOFIA, an infrared telescope mounted in a modified Boeing 747, had discovered water in Clavius crater. Clavius is located at a latitude of 58 degrees south, which is nowhere near the pole, and is subjected to the full strength of the sun's light each lunar day. In these conditions, water should rapidly sublimate away, yet there it was in broad daylight. It wasn't much, about 1% of what you would find in the sand of a typical terrestrial desert, but the existence of even that much was deeply weird. It's now believed that the sunlit water survives thanks to one of two mechanisms. It may be trapped within glass like beads created by micrometeorite impacts, or it could exist in tiny microscale cold traps created by the shadows cast by individual grains of the lunar regolith. Either way, this discovery opens a new range of possibilities for where we might want to go hunting for water on the moon in the future. So, here's a quick summary of the state of the hunt for lunar water as it currently exists. So, we know that PSRs do in fact exist on the moon and are sufficiently cold to support the long term storage of water and other volatile molecules. Despite this strong theoretical backing, water does not appear to be as abundant as it could be. Rather than large surface exposed ice or deposits, any ice that does exist is likely buried in the subsurface, mixed in with the regolith, or at spatial scales below the resolution of our orbital data. Now, looking towards the future, there are still several questions that have yet to be resolved. First, we would like to understand why water appears to be relatively scarce on the moon. Water abundances do not seem to be limited by the available cold trapping area, since most of the cold traps seem to have little to no water in them. This contrasts with Mercury, seen here, whose PSRs do appear to be filled with exceptionally thick deposits of ice. What causes this difference? Perhaps it's something as simple as a difference in delivery sources. If Mercury had, for example, a major cometary impact in the recent past that delivered a large volume of water, then it wouldn't be surprising that there is more water in Mercury's PSRs. It could also be that there is something more fundamentally different about PSRs on the Moon and Mercury. Maybe Mercury is more efficient at transporting water from its delivery sources to the poles of the Moon, or maybe the Sun is better at destroying water molecules at the Moon than at Mercury for some reason. Second, we don't yet fully understand the role that small scale terrain features play in the cold trapping of water. Theoretical models have shown that surface roughness and small craters on scales down to about 10 centimeters can create cold traps that are unresolved from orbit, increasing the total area available for the cold trapping of volatiles. As previously mentioned, this is a potential explanation for the Sophia results, but it could also have a role around and even within the PSRs, creating small areas that are protected from both direct and scattered sunlight, which would make them even colder than we've measured from orbit. We are unlikely to be able to answer this question without getting down to the surface ourselves, either with humans or with rovers or landers. And this is actually what I did my master's research on. So if you have any questions for after we are done here, please do ask them in the chat. So let's now turn our attention to the future and some of the current and upcoming missions that will continue the search for lunar water. So here is a quick overview of what we can look forward to through the end of this decade. Note that this is certainly not a complete list. I would not be surprised to see it expand in the coming years as some of these missions make new discoveries. So the first few here are missions that were launched in the last few months. We'll begin with the Korean Urey spacecraft, which carries an instrument called ShadowCam. As its name suggests, ShadowCam builds upon the PSR direct imaging campaigns carried out by Kaguya and LRO. The major difference between ShadowCam and TC and LROC is that the ShadowCam was specifically designed to work in the low illumination environment of PSRs, while TC and the NAC were not. In order to image the interiors of PSRs, TC and NAC had to dramatically increase their exposure times, which resulted in pixels getting smeared across the spacecraft's direction of motion, which severely hurt their resolution compared to images that they took of the illuminated terrain. ShadowCam is about 200 times more sensitive to light than either TC or NAC, meaning that its exposures can be much shorter, resulting in an appreciably higher resolution. We can see an example here comparing images of the same region taken by LROC NAC and ShadowCam. ShadowCam reveals all kinds of small details that are not visible in the NAC images, including small craters and boulders in whose shadows ice could be hiding. The ultimate goal of ShadowCam is not just image PSRs at an unprecedented resolution of 2 meters per pixel, but also to track how potential ice and frost changes on the surface over time, something that has never been possible up until this point. The next two missions were launched as ride along secondary payloads on the Artemis 1 mission. So, Artemis 1 carried 10 of these small form factor CubeSats, each about the size of a briefcase. They were mounted inside one of these stage adapters, which is located just below the Orion spacecraft here, and were released once Orion had separated for its journey to the moon. The two that we are interested in here are the Lunar Polar Hydrogen Mapper, or Luna HMAP, and Lunar Ice Cube. So, Luna HMAP is a neutron spectrometer, much like LPNS and LEND, but was planned to orbit just 5 kilometers above the surface. For comparison, Lunar Prospector orbited at an altitude of 100 kilometers, and our LRO's orbit has varied between 20 to 165 kilometers. This much lower orbital altitude would have allowed Luna HMAP to construct much higher resolution neutron suppression maps, helping to resolve the question of whether or not LEND did actually achieve its claimed resolution, and potentially allowing us to map specifically where in each PSR subsurface ice deposits might exist. Unfortunately, shortly after launch, a valve in the spacecraft's propulsion system became stuck, and it failed to enter lunar orbit. The Luna HMAP team has been attempting to troubleshoot the problem since November, but it is unfortunately believed that the mission will become unrecoverable in the next few weeks. Although the precise cause of the malfunction is not yet known, it is speculated that it is a consequence of the 3-month delay to the Artemis 1 launch date, as Luna HMAP's propulsion system was not designed to sit prepared but idle for that length of time. The other Artemis CubeSat sent to search for ice is Lunar Ice Cube, an IR spectrometer like the one on M Cubed. The one carried by Lunar Ice Cube is derived from the one carried by New Horizons, but scaled down to 1/6 of its size to fit into the CubeSat body. Lunar Ice Cube's goal is to study the full lunar water cycle, including both the storage of water within the PSRs as well as the transport of water through the lunar exosphere. This is important because the exact mechanisms through which water is transported from its delivery sites to the PSRs are not entirely well understood, existing mostly as theoretical models with little available data to back them up. Unlike Luna HMAP and many of the other Artemis CubeSats, Lunar Ice Cube fortunately does not appear to have suffered any post-launch anomalies, and we are all looking forward to seeing its first results. The next mission here is Lunar Flashlight. It was also intended to be an Artemis 1 ride along, but it missed its integration deadline, forcing it to find another ride to space. It eventually found a spot alongside the Hakuto R Mission 1 spacecraft, which attempted to land on the moon several weeks ago. Lunar Flashlight is like a combination of Lola and M Cubed, taking active reflective measurements using a near IR laser and spectrometer. Unfortunately, missing the Artemis 1 ride did not exempt Lunar Flashlight from the Lunar CubeSat curse, and it too experienced post-launch thruster issues similar to those of Luna HMAP. If the team had examined different modifications to the mission that would still allow it to achieve some of its goals, including placing it into a high Earth orbit that would let it scan the lunar poles once a month. However, the problems with the propulsion system were not solved in time to place the spacecraft in this modified orbit, and NASA terminated the mission on May 12th. Lunar Flashlight made its last close flyby of Earth actually last night, and is now headed off into interplanetary space. Next up is the Intuitive Machines 2 mission, which will be the third of NASA's Commercial Lunar Payload Services program. The primary payload of this mission will be the Polar Resources Mining Experiment 1, or Prime 1. Prime 1 will carry 2 instruments, the Regolith and Ice Drill for exploring new terrain, Trident, which is a drill that will be used to extract samples down to about 1 meter below the surface, and the Mass Spectrometer for observing lunar operations, or MSOLO, which will be used to analyze the samples drilled by Trident. Accompanying Prime 1 is a secondary payload called Lunar Trailblazer, which is a small lunar orbiter that was constructed as part of NASA's Small Innovative Programs for Planetary Exploration, or SIMPLEX program. Lunar Trailblazer's science objectives are to map the location and abundance of water ice on the moon, as well as to track how those ice abundances change with surface temperatures over the course of a year. It will do so using two instruments, the High Resolution Volatiles and Minerals Moon Mapper, or HRVM cubed, and which is an infrared spectrometer similar to the one used by M cubed, and the Lunar Thermal Mapper, or LTM, which will be used to map surface temperatures at a higher resolution than is possible with the Miner. And IM2 is currently expected to launch in November of this year. 1 year later, in November of 2024, NASA is expecting to deliver its Volatiles Investigating Polar Exploration rover, or VIPER, to the South Pole. I would call VIPER the star of NASA's uncrewed lunar program, as it will be the first time that a rover will be sent to conduct a semi-autonomous search for water ice on the moon. VIPER's 4 instruments will consist of an infrared spectrometer to look for surface exposed ice, our good friend, the neutron spectrometer, to look for subsurface ice deposits, a 1 meter drill to sample any subsurface deposits, and a mass spectrometer to analyze the contents of the drilled samples. VIPER is targeted to land in this area on the rim of Nobile crater. Although this landing site does not contain any of the large PSRs, if we zoom in, we can see that there are a number of smaller shadowed areas here, which VIPER will be able to briefly dip into to sample their contents without putting itself at too much risk. This is important because VIPER will be solar powered. Getting stuck in a large PSR would likely result in mission termination because the rover would not be able to leave to recharge its batteries. The VIPER mission is planned to last for 100 Earth days, during which time all kinds of operational challenges will be tested, including near real-time interactive rover driving, plotting complex routes to avoid shadows wherever possible while maintaining a direct line of sight to Earth, and withstanding days of darkness when the temperature can drop by hundreds of degrees when the sun sets. Of course, the mission that has everyone excited is Artemis 3, which will mark the first time that humans have set foot on the moon since Apollo 7 in 1972. Because Artemis 3 is not scheduled to launch until December 2025, the mission details have not yet been finalized, including the landing site. This here is a map of all of the candidate landing sites, illustrating how exploration of the PSRs is clearly a priority. The crew will stay on the surface for nearly a week, which is longer than any of the Apollo missions, and will be able to conduct expeditions to nearby PSRs using a rover that will be delivered to the landing site in advance. As a Canadian speaking here on the invitation of the Royal Astronomical Society of Canada, I decided that it would be appropriate to finish this talk with the Canadian Lunar Rover Mission, or LRM, the first time that an almost exclusively Canadian designed and Canadian built spacecraft of this size will be sent off to explore another world. This mission, consisting of a rover to be sent to the South Pole, is a major part of the Canadian Space Agency's Lunar Exploration Accelerator Program, or LEAP, whose goal is to develop the future of the Canadian space economy by funding innovative science and technology ideas with applications in and around the moon. The design of the main rover body is contracted out to the Canadensis Aerospace Corporation, which is headquartered here in Toronto. While construction of the rover, including 5 of its 6 science instruments, will be handled by both industrial and academic partners from across Canada, some of which are indicated here on this map. So LRM will carry 6 instruments with it, 5 of which will be provided by Canadians and 1 by NASA. Unsurprisingly, one of these instruments will be a neutron spectrometer, named the Lunar Hydrogen Autonomous Neutron Spectrometer, or LHANS. LHANS is currently under construction at Bubble Technology Industries in Chalk River, Ontario. In addition to the rover body, Canadensis will be providing a suite of 3 instruments, collectively referred to as the Frozen Regolith Observation and Science Tools, or FROST, which is an appropriate name as their primary goal will be to look for ice frost on the surface. It will do so using a Lyman alpha imager similar to LAMP, but on the surface rather than from orbit, as well as 2 multispectral imagers that will study the mineralogy and the reflectance of the regolith. Teledyne DALSA from Waterloo will be providing a radiation microdosimeter that will measure the radiation environment experienced by the rover. This will be important for future long-term crewed missions to the moon, as any lunar base will not be protected from solar radiation by Earth's magnetosphere. The final NASA-funded instrument to be provided by the Johns Hopkins Applied Physics Laboratory is the Lunar Advanced Filter Observation Radiometer for Geologic Exploration, or LaForge, which will examine surface temperature at small scales. And LRM is currently scheduled to launch no earlier than 2026. So to take a bit of a closer look at the Canadian Lunar Rover mission, I'll just take a look at this brief video that was produced by the CSA. So we are clearly living in a very exciting time for lunar exploration, but unfortunately, all things must come to an end, like this presentation, as that is all that I have for you tonight. So if you want to find me elsewhere, here's where the two places you can find me on Twitter. And so thank you for your attention, and I look forward to taking any questions that you might have.
Oh, thank you so much, Connor. As you say, water, water everywhere, and now maybe the moon too. So I guess the moon isn't just in charge of pushing around water in our own oceans. It seems like there's just so much going on. We're looking over to YouTube for any questions, but while we're waiting, I'll actually go ahead and maybe sneak in one for myself. One of the things that we're always interested in with water, and when we're talking about water on the moon, how does this compare to water that we see on Earth? Do you know?
In terms of quality or quantity, or
Yeah, or drinkability?
yes, this is definitely a very important question that will have to be answered. Unfortunately, I don't think it's one that we really know very much about right now, just because a lot of what we have, you know, the way that we've looked for water on the moon so far has been almost exclusively from orbit. So we can't actually, say much about the actual, the quality of the water that we might find or whether or not it might be drinkable. So that's really a question that will have to be answered, by us actually going down to the surface, either with one of these rovers or when we send humans back to the moon with Artemis 3.
Excellent. Well, thank you. And I just have one more, I suppose, maybe quick question. Given the water that we've seen you describe so far, how easy do you think it would be to extract the water from the moon rocks?
Yeah, I mean, again, it's one of those things that will be most easiest to answer after we actually go down and look for the water. I think with the IM-2 mission, that's going to be sort of the first test of actually going down to the surface and trying to actually, extract and use these resources for the first time in advance of actually sending humans there. Um, so yeah, it definitely depends. If it's just like a small amount of water, absorbed to the surface, or as a frost, it's probably going to be more difficult than if there's large, you know, blocks of ice either on the surface or in the subsurface. So again, we need to go to the moon again and find this stuff out.
I agree wholeheartedly. I can't wait. I mean, of course, we do have to wait. We have Artemis 2 coming before Artemis 3 gets there.
Mhm,
And I mean, you were talking about Canadian space. And so, of course, extra props to Canada with Jeremy Hansen going even on Artemis 2.
mhm.
And it's a very exciting time, as you say. Now, we'll go ahead and go on to our next question. We have one from Betty saying, I wonder how the craters were chosen as targets for research.
So yeah, I mean, a lot of the target selection, the craters, specifically like for like the Artemis missions, that those landing sites. I mean, a lot of it is based on that orbital data that we have. Saying here is where water might be, here's where water might not be. Um, in terms of research in general, the really great things that these orbital studies are able to actually map basically the entire moon. So we don't need necessarily to select a specific crater or not. We can just image the entire region and see what we see. Of course, the trade off there is that you can either have wide coverage or you can have high resolution. So even though these maps do cover a large region of the moon, we do have that problem of them being not particularly high resolution, which does impact our ability to see what's going on at these sort of small human scales.
Yes, I love the idea of the small humans also being involved with this moon exploration. So it looks like we have one more question from Ron McNaughton. How cold does the deepest crater get? I heard it was the coldest place in the solar system. Is that true?
They do get phenomenally cold because PSRs, they don't expose they're not exposed to any direct sunlight, which is the primary source of illumination and thermal energy on the moon. And within the PSRs, as I mentioned, there might be these really small regions that are protected from both the direct and single scattered sunlight, and those are in fact some of the coldest places In the solar system, potentially getting down to 40, 30, 20 Kelvin even. The problem with, when you get that cold, it becomes increasingly hard to actually measure those temperatures. So, for example, Diviner, which has been used to map temperatures of the moon, really sort of starts to lose some of its precision in that range. So it's actually, so cold that we almost can't even measure it reliably. But yes, definitely one of the coldest places in the solar system.
Excellent. Well, you heard it all here, folks. The moon is definitely a well, I won't say hot, but cool destination to get to. I think that's probably about all the questions we have time for tonight. So I'll just go ahead and wrap up a little bit. But thank you once again, Connor. I think that this is, as you say, a really, really exciting time to be looking up and, of course, looking towards the moon in particular, and of course, Mars after that, obviously. So we'll go ahead and wrap up for tonight. Thanks again to our wonderful speaker, Connor Hayes. And we'll go ahead and hand over to the president of the Toronto Rask Center, Tom Luton, to finish off the evening. Over to you, Tom.
All right. Well, thank you very much, Elena, and thank you very much to our speaker. Good evening, everyone. Hope you're doing well. So, we've got some announcements. Let's get going. So, for those of you who are joining us, perhaps for the first time, welcome. This is one of two types of meetings that we have here, online for some, or online for all, and in person for some, here at the Toronto Centre. We've just had one of our speakers' nights, and at the beginning of June, we will be having one of our recreational astronomy nights. If you're joining us here live on YouTube, please say hello in the chat. Enter some questions for the presenters, as others have done. If you're a new member, please introduce yourself to the rest of us. And if you're coming to us from far, far away outside the Toronto area, let us know where you're coming from. So our next recreational astronomy night is coming up on the 7th of June at 7:30 p.m., both in person at the Ontario Science Centre and online here on YouTube. Chris Vaughn will be discussing the sky this month. Dennis Drey will be reporting on the Northeast Astronomy Forum, and Arushi Nath will be discussing the DART mission, Did We Move Asteroid Dimorphos, and briefings from the Planetary Defense Conference of 2023. With an online delivery here, youtube.com/rasktoronto/live. And if you got something you'd like to present, please contact Paul Markov. Now, our speakers' nights have wrapped for the summer season. So our next speakers' night will be in September. Coming up later in the month, for this month's Bayview Village Park City Star Party will be the first clear night of next week, May 22nd to the 25th, excluding Wednesday. So even if Wednesday is clear and it's the first clear night that week, it will not be on Wednesday from 8 p.m. to 11 p.m. Please check out our website for go, no-go decisions, whether regarding the weather or whether or not the event will actually take place. And then coming up on Friday, May 26th at 6 p.m. is the Millennium Square Public Stargazing event. So join us for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square in Pickering. Take a look at the moon, stars through our telescopes that we provide. Check out our astronomy literature at our info booth and ask us some questions about the stars and the planets. You can bring your own telescope. We'll be happy to help you set it up and aim it at the moon. Just a reminder that the weather is cooler down by the lake, and we're still recommending folks wear masks at these events, and also we'll have some hand disinfectant around before handling all of our equipment and material at the information booth. Again, check our website for a go, no-go decision before heading down to the square. At the DDO coming up on the first clear night of the week of May 29th to June 2nd is our DDO stargazing night, starting at sunset. There's no registration required for this event. Just come on over. Then on Saturday, June the 3rd, is Astronomy Family Night. from 10 o'clock to midnight. Um, there are some fees for people up to the age of 14. It's $15.69. For people 15 or older, 17.72. You have to register online for this one. Links can be found at rascto.ca. Planetarium Day is Sunday, June 4th, 1 p.m. to 4 p.m. Uh, Registration fees are 15.46 up to the age of 14, and 15 and older $17.47. Registration online, links again at rascto.ca. The CAO is open to members. We're still keeping some COVID restrictions in place, so access to CAO facilities by members and families only in a modified communal fashion with the total site occupancy limited to 25 individuals. The upstairs washroom is only for upstairs bookings with the max occupancy for the upstairs bedrooms of 2 from the same family per bedroom for a total of 6 people. Communal areas limited to 3 people wearing masks. All CAO users can use both kitchens, the downstairs washroom while wearing masks. Full details are on the website. Please read everything before making your bookings. Now we're trying to fill some job postings here. One of the things we're looking for is a chief editor for Scope, our club newsletter. So if you like to edit and write, we're hoping to get this out on a bi-monthly basis, and it's distributed to everyone in the Toronto Center. Please contact myself, volunteer coordination, at volunteer@rastio.ca if you're interested. We're also looking for an education and public outreach chair, a light pollution committee chair, and a volunteer committee chair, as well as a marketing committee chair and forming a marketing committee. The Education and Public Outreach Committee is always looking for additional help, especially online presenters and telescope camera operators for virtual star parties. Just a reminder that to volunteer, you must first be a member. So drop me a line at president@rascto.ca. Brief plug here for the benefits of membership. If you like what you've seen and would like to join us, you can sign up online, or you can renew your membership at secure.rasc.ca. And gift memberships are also available. Contact the national office at mempub@rasc.ca. And with that, I'd like to wish you all a very pleasant evening. I want to thank you very much for joining us. Please follow us on all the social media sites that we've got listed here. If you like what you saw here on YouTube, please like and subscribe and hit the notification bell. Be safe and keep looking up. Good night, everybody.